Hi, welcome back to Physics 123, the video series. Today we're going to talk about fluid dynamics. Now, fluid dynamics is an interesting, crazy topic. You can do some pretty weird things with fluid dynamics. If you're familiar with chaos theory, you may know that chaos theory was started by some people who were studying what they thought should be fairly simple fluid dynamics problems. So fluid dynamics can explode and do marvelous, wonderful things. But we're going to just look at the very basics of fluid dynamics, so we're not going to deal with chaos in this class, unfortunately. So we're just going to start with some basic things. We're going to work with two equations, and one equation is known as the continuity equation. All right? In the continuity equation, basically, it's conservation of mass. So the one assumption we have to make in order to get the continuity equation is that the fluid is incompressible. Did you get that? Very important. The fluid is incompressible. That means if I take some of this fluid and I squish it with a high pressure, the volume doesn't change. The density does not change with pressure. Water is a good example of a very good approximation to an incompressible fluid. The density of water at the bottom of the ocean is very similar to the density at the top, other than effects due to temperature. All right, pressure, you have to put a lot of pressure on water to change its density even a tiny amount. So that would be an example of something where the continuity equation applies very well. Air, if it's moving slowly, it tends not to compress too much, and this equation would be true. If the air is moving quickly and being compressed very quickly, you can have the density change significantly, and then you would not want to use this equation or not expect this equation to give extremely accurate results. Okay, so there is our approximation. There's our assumption. It's always important to know what your assumptions are so that you know when you can actually use the equation. Now, what is the equation of continuity? Where does it come from? Okay, what I've got here is a depiction of a pipe, and that pipe narrows down, all right? So imagine we have this pipe, and I've got some incompressible fluid like water flowing through it. If the fluid is incompressible, that means that if I put some mass in this side, that same mass has to come out that side. It's got nowhere to go, right? I can't build up mass inside here because the fluid is incompressible. All right, so the equation of continuity basically starts with the idea that mass in is mass out for an incompressible fluid. Okay, so let's imagine that we have our fluid flowing and we watch it flow for some time tau. And in that time tau, a little mass, the fluid moves a little bit on this side and a little mass flows in. On the other side, a longer cylinder of fluid is going to flow because this fluid has to have the same volume as that fluid, right? Because they both have the same density, and whatever mass flows in has got to be the mass that flows out. All right, so I'm going to call the height of this little cylinder delta x1. How's that? And this one right here, I'm going to call its length delta x2. All right? So basically, the equation of continuity says that mass in is equal to mass out. The mass going in is just the cross-sectional area times delta x1. That's the volume, right? So let's multiply that by the density. There's the mass that flows in this side. That's got to be equal to the mass that flows out the other side, which is density times the volume of the cylinder, which is area 2 times delta x2. All right? But then we can say, well, if my fluid flows for some time tau, delta x1 is just going to be velocity times time. So I can write this as density area 1 times velocity 1 times time tau. And on the other side, I can write this as density area 2 velocity 2 times time tau. Now, if I cancel out the tau, so I cancel out the density, which is the same on both sides, I'm left with area 1 v1 velocity 1 is equal to area 2 velocity 2. And this is the continuity equation. All right? So for example, since I said water is a fairly incompressible fluid, you would expect that this equation would apply to water going through a garden hose. So you get your garden hose and you put a nozzle on the end of it to make the water come out faster, right? Well, if you know the cross-sectional area of the hose and the velocity of water in the hose, you know the cross-section of the nozzle, then you can use this equation to find the velocity of the water coming out of the nozzle. All right? Really handy equation. Okay, but what if you know the cross-sectional area of the hose and the nozzle? You can measure those, and you want to predict how fast the water will be coming out. All right? but you don't know the velocity in the hose. How could I possibly find that? Well, there's another equation we're going to be using in this unit, and that's known as Bernoullis Equation, and that will finish our puzzle for us. And here is Bernoullis Equation. It says that the pressure plus 1/2 density velocity squared plus density GH is constant. All right, so first of all, of course, P is pressure, rho is the density of the fluid, and just like with the continuity equation, we are going to assume that the fluid is incompressible, so the density of the fluid is going to be the same everywhere in the flow. All right, G is the acceleration due to gravity. So here is a second approximation we're going to make when we derive Bernoullis equation. We are going to assume that the acceleration due to gravity is constant. All right, okay, and H is the height of the fluid flow. All right, so we look at some point in the flow. This is how high that thing is from some arbitrary reference point. It can be the height from the ground, the height from the center of the earth. It's completely arbitrary, okay? And you'll see why in a minute. But before we talk more about this, I'm going to talk about some of the questions I had when I was an undergraduate taking this course and learning about Bernoullis equation. The thing that popped into my head as soon as I saw Bernoullis equation was, what is the constant? This thing is equal to a constant. What is the constant? Is it 14? Is it pi? Is it the speed of light? I mean, what constant is it? And finally I realized it's not like some fundamental constant. It is a constant for the flow. So for any given flow in some pipe, there will be some constant that describes that flow. All right? A better way to say this, and a better way to think about Bernoullis equation, in my opinion, is to write Bernoullis equation this way. What we mean when we say this is equal to a constant is it means if we evaluate this at some point in the flow, point 1, and if I evaluate it at some other point in the flow, point 2, I'll get the same thing. All right? So if I go to my pipe here and I measure the pressure, the velocity, and the height right here, I measure the pressure, the velocity, and the height right here, all right? Then if I take that pressure, all of this stuff for point 1, and I evaluate the same thing for point 2, those will be equal to each other. All right? So that's what we mean when we say it's a constant. That if you evaluate that value at any point in the flow, it will stay the same. It'll stay equal to the same value everywhere through the flow. Okay? So that's what the constant is. All right? Now, this is really useful, right? Because it relates the pressure, the velocity, and the height at 2 different points in the flow. So if we look at our garden hose, for example, right? I don't know the velocity inside the hose, but if I can know the pressure inside and outside the hose, right? And I know the height of the hose and I know the height of the nozzle, all right? I can relate, then I have an equation that relates to 2 velocities. And I've already got another equation that relates to 2 velocities, so now I've got 2 equations, 2 unknowns. All right, so if I can use other equations or other information to find any 5 of these 6 things, I can find the 6th one. All right? Okay, now, there's 2 other questions we need to address. First of all, where did this equation come from? It's just out of the blue. All right? It turns out that until we get to the modern physics section, we're really not going to learn anything new in this class. We're just going to do applications of things you learned in Physics 121, all right? So we ought to be able to come up with this equation using Physics 121 ideas, and that's what we're going to do. The other thing you should be asking yourself is, what are the assumptions that were made when this equation was derived? That's important, right? The continuity equation, I said, the only assumption we made there was that it was an incompressible fluid. So I know that if I do use that equation with a fluid that's compressible, I'm not going to get accurate results. When can I use Bernoullis equation and get accurate results? To know that, I need to know what the assumptions are. So we're going to do the derivation now. In the process of doing the derivation, we're going to learn what the assumptions are. And so you'll know when you can use this equation. I could just tell you the assumptions, but you'll understand them better if we actually do the derivation. Also, by doing the derivation, you're going to see a cool example of how you can use Physics 121 material to figure out Physics 123 material. You will learn how to set up problems. You'll get an example of how to set up a kind of a difficult problem and then easily solve it. All right? Also, If you understand the derivation, you will understand Bernoullis equation. Many, many times I've had students go into exams and they get confused, right? They're used to just plugging things into equations. They look at this equation, and I've seen crazy things where they saw the density and it kind of looked like a P, so they plugged in pressure, right? Or things that are a little more subtle that students did, that they made mistakes that they would not have made if they really understood what Bernoullis equation meant. And we get that understanding by going through the derivation. It's like my karate instructor likes to say, practice hard, fight easy. Right? When you're in the middle of the fight, you don't want to be thinking about what you're doing. You're not going to do your best then because you're under stress. So you need to practice harder than you're going to need to defend yourself in a fight. Same thing happens with physics. If you want to be able to work problems like the homework problems, but stressed and frightened in a testing center environment, you need to understand the problems better than you need to just work them on the homework. And I think this derivation will help you. All right, so let's derive Bernoullis equation now. So imagine I've got some incompressible fluid flowing through a pipe. All right, so my first assumption is it's going to be an incompressible fluid. And the reason for that is we're going to assume that if I shove some mass in one side, that same mass comes out the other. All right, so we're going to use some of the same logic we used for the continuity equation, but we're going to do something different. So imagine, if you will, all right, I've got fluid flowing through this pipe. All right, now the continuity equation tells us that the velocity up here, right, since my cross-sectional area is larger, the velocity is going to be slower here than here. All right. Also, so the velocity is going to be different. Also, the height is different. Okay, so there's going to be pressure. So imagine, let's ignore all the fluid. Let's just kind of imagine this little piece of fluid here between these 2 points. All right. As this moves from here to here, right? So the whole thing translated a little bit. Things changed. All right, because when the fluid moves from here to here, it's as if I took a little piece of fluid here and moved it up here. But this little piece of fluid now, it has a different velocity and it has a different gravitational potential energy. All right? So what was it that provided the force to change the height and to change the velocity? It's the pressure pushing on this column of water. But of course, there's not just pressure pushing it up and speeding it up. There's also pressure on this side pushing it down and slowing it down. All right? Okay, so how can we solve this problem? We could integrate forces to find how velocities change and things like that. All right, but that would be a lot harder than what I plan to do. So instead of doing that, let's go back to Physics 123 and let's think of a Physics 123 mechanics problem. Imagine I have a pendulum. I have some mass over here. I'm going to let it go. It's going to swing down and come over here. And here it's not moving, but by the time it gets to the bottom, it's traveling at some velocity. All right? Let's call the pendulum, so the pendulum has a length L. Right? What is the velocity of the mass when it hits the bottom? We could, once again, we could integrate forces to find velocities as it's moving through this arc. But that's really hard. There was a trick we used for problems like this in Physics 121 that made these problems easy. What was that trick? Do you remember what it was? Think for a minute. Were you thinking conservation of energy? I know I was. Yeah, conservation of energy. So conservation of energy is what is going to make this problem very simple. So we just, hold on. I got a phone call. Just a minute. Sorry about this. Hello. Hey, I was just going to see your boss. Tell him I've got this money. Yeah, but this time I've got the money. I don't have it with me. Tell Jabba. Hey, even I get bored sometimes. Do you think I had a choice? Over my dead body? Yeah, I bet you have. Sorry about that mess. Hopefully we won't get interrupted again. Anyway, we were talking about this pendulum and how we can use conservation of energy to make it really easy, right? We just look at this and we say at the top there's no kinetic energy, but there's a potential energy, which is mgl, right? If I assume I'll let height be 0 right down here, okay? At the bottom, we're at h equals 0, so there's no potential energy anymore, but we have kinetic energy, which is 1/2 mv squared, right? And we know that energy is conserved, so the energy at the top needs to be the energy at the bottom, and it's really easy to find the velocity at the bottom. Okay? We're going to do something very similar with our pipe right here. Okay? So we can use the continuity equation and the ideas there, the incompressibility of the fluid, to relate how far the fluid moves down here to how far it moves up here when we push this column of fluid up. And then we're going to say, well, look, once I push this column of fluid up, I've effectively transferred this little piece of fluid up here. Okay, really I haven't, right? I've moved this fluid over here and moved this one over here, but the effect is the same as if I've taken this one up here and moved it up here. But now it's at a different gravitational potential and it's moving at a different velocity. So we're going to use conservation of energy. So initially, on the left side, the fluid has a kinetic energy, which is 1/2 mv1 squared, and it's got a potential energy, which is mg, the height of the left side of the pipe. All right? On the other side, we've got kinetic energy, which is 1/2 mv2 squared, and a potential energy, which is mgh2. All right? Very simple. Now, are those two equal to each other? Well, not necessarily, because there is work being done as the fluid flows, right? There's pressure pushing on this side trying to speed it up and move it up, and there's pressure on this side trying to slow it down and push it down, all right? But the difference in the energy at the top and the bottom, the difference between this and this, must equal the work that's being done. So what is the work being done? Well, there's positive work being done at the bottom and negative work being done up here. The positive work, right, work is force times distance, assuming the force is constant, so we don't have to do an integral, all right? So the total work, there's going to be work done at the bottom, which is the force at the bottom. The force at the bottom is pressure 1, area 1, and the distance is delta x1. All right, and then there's negative work being done at the top, which is the force, pressure 2, area 2, times the distance, which is delta x2. All right? Very good. And that all has to be equal to the difference between this and this. So 1/2 mv2 squared plus mgh2 minus 1/2 mv1 squared minus mgh1. All right? Okay. Now, I don't want delta x1 and delta x2 there, all right? I want to get this into something more fundamental for the flow. So I'm going to note what we noted with the continuity equation, right? That the mass that flows in on the left is just the density times the volume. And what's this volume right here? It's just the cross-sectional area times delta x1. So the volume is just going to be area 1 delta x1, all right? Okay, so it's also equal to density area 2 delta x2, right? So what I'm going to do, instead of getting rid of delta x1, I'm going to replace mass over here with this, all right? And then we'll see how everything works out. So I'm going to take this over here. I've got pressure 1, area 1, delta x1, minus pressure 2, area 2, delta x2, and that's got to equal 1/2, and for mass I'm going to put rho area, since this is 2, I'll use this one here, rho area 2 delta x2. All right. No, you know what? This is going to work easier if I replace delta x1 and delta x2 with mass. So let's do this. So the work is going to be pressure 1, area 1, and then delta x1 is just going to be mass divided by rho area 1, minus this thing right here, pressure 2, area 2, and then delta x2 is just going to be mass divided by rho area 2, and that's got to equal 1/2, it's got to equal this thing right there, all right? When we do that, notice the area 1 cancels out and area 2 cancels out, all right? And what else happens? If I look, I have a mass here, here, I have mass in all of these terms right here. So if I multiply through by rho, we'll get Bernoullis equation. So we get pressure 1 minus pressure 2 is equal to 1/2 mv2 squared plus rho v2 squared, right? We got rid of the masses, but then I had to multiply through by rho. So it's rho v2 squared plus rho g h2 minus 1/2 rho v1 squared minus rho g h1. And if we take all of the 1 stuff to one side and the 2 stuff to the other side, we'll get pressure 1 plus 1/2 rho v1 squared plus rho g h1 is equal to the same thing but with 2. All right? And there's Bernoullis equation. We derived it. Okay? Now, thing to note. What we did is we set the work equal to the change in energy. The work involved pressures, right? And then we looked at the kinetic and potential energy for the little pieces of fluid. But then to solve things, we ended up basically changing masses into rhos, right? So when I canceled out the mass and then multiplied through by rho, so I multiplied, basically what it is, I multiplied by rho over m, that's just 1 over the volume, right? Because density is mass per unit volume, right? Yeah? So I basically just divided by volume. So what that means is, this right here, that is the kinetic energy of the fluid per unit volume at the one side. And this is the gravitational potential energy per unit volume at side 1. All right? So these are just energies per unit volume. Pressure, turns out, has units of energy per unit volume. That's another way to think of its units. So you can think of pressure as like a potential energy to do work on the fluid. And Bernoullis equation is just conservation of energy. So now, hopefully, you can always write down Bernoullis equation without ever having to try to memorize it at all. Just remember pressure plus kinetic energy per unit volume plus gravitational potential per unit volume is going to be constant along the flow. Okay, so now we know where the equation comes from. This would be a good time to pause the video and see if you can do that same derivation. And keep watching it until you can, and then you will really understand Bernoullis equation. Like I said, we won't do derivations on the homework, but the problems we work on the homework will come very easily to you if you understand the derivation of Bernoullis equation. So pause the video, go do it, okay? And you're back. Good. You understand the derivation, I hope. Okay, but now, what assumptions did we make when we derived it? When is this valid? Well, first, we assumed that the fluid was incompressible, right? That the mass in was equal to the mass out. So incompressible flow, same as the continuity equation. But whereas the continuity equation only had that one assumption, we made some other assumptions. One thing we assumed is that the acceleration due to gravity was a constant. That's usually a pretty good assumption for things here on the surface of the Earth. Gravity doesn't change much over the height of most fluid flows. All right? Another thing that we assumed, though, was that we had taken into account all sources and sinks of energy, right? This was conservation of energy, and we assumed that pressure did the work, and then we had potential energy due to gravity and kinetic energy, and that was it. Kinetic energy due to the flow. Well, it turns out there's some other interesting things that could happen in a flow. So imagine I have a flow, right? And I have these, imagine I put some little particles and I track how the flow moves, and I see my fluid flowing, right? This is what's known as a laminar flow, because the flow lines don't cross. The flow kind of makes sheets, all right? But it turns out it's very common in flows for things to become unstable and have flow lines that do little circles and eddies. Call this turbulence, all right? Turbulence is motion of fluid which is not characterized by the net motion of the fluid along the flow. So this velocity right there does not take into account the swirling motion of the fluid. If there's swirling going on, there's extra kinetic energy in the swirling, right? And in fact, that swirling tends to move velocity, tends to move energy to smaller and smaller scales until eventually the fluid actually heats up, and some of that energy turns into heat, all right? So we intrinsically assumed that the fluid was irrotational, that it was a laminar, what we call a laminar flow, where the flow lines don't cross and they don't spin and do weird turbulent things, all right? So a non-turbulent flow, a laminar flow, is one of the assumptions of Bernoullis equation. Another thing which we neglected was possible friction. As this flow goes past our pipe, right, it's going to have some forces with the surface of the pipe which could slow it down. So we assumed no friction. In fluids, we use the term viscosity to describe friction. Viscosity tells us how much friction there will be between the fluid and the things that it runs past, or things that run through it. So we assumed no viscosity, all right? Ironically, viscosity is what stabilizes a fluid against rotational flow and turbulence. So it's kind of counterintuitive then to say we're going to have no viscosity and no turbulence, all right? But it turns out that there are times when the viscosity is low enough and the turbulence is low enough that Bernoullis equation is valid, all right? One particular case is when the velocity of the flow is 0. All right, let's consider Bernoullis equation when there's no kinetic energy term. I'll just get pressure 1 plus rho g h1, and there's no velocity, so the other term is gone. That's equal to pressure 2 plus rho g h2. All right? Then there's no turbulence because there's no flow. And I don't have to worry about viscosity. There's no friction if nothing's moving, all right? So there's a case where Bernoullis equation works really well as long as we have an incompressible fluid, all right? I brought this up because imagine if you have a lake. Here's a cross-section of our lake, and you want to know the pressure some distance h below the lake. All right, we derived this before. The answer we got is embedded in Bernoullis equation. That's really cool, right? So let's do this. So let's let pressure 1 be atmospheric pressure, and let's let height 1, let's define this to be h equals 0, so that term goes away. Pressure 2 is the pressure some depth below the h, and h2, right, normally h goes up when we move up, all right, and now we're having h increase as we go down, so h2 is going to be minus the depth below the surface, and so our equation becomes P naught is equal to pressure at some depth h minus rho g h. Move this to the other side, and we get then the pressure below the lake is just atmospheric pressure plus rho g h. We saw this result before, right? It's kind of cool to see that it's in Bernoullis equation. This is an example of an awesome way to check your answers. When you're working the homework, you will ask students, other students, did I do this right? Am I doing this right? You'll ask TAs, am I doing this right? Is this the right way to do this? When you take the test, you will not have the advantage of being able to ask people if you're doing it right. So I recommend, as you work the homework, that you practice ways to check your work. And there are things you can do. You can check units. Units is a great way to find errors. If you don't have the right units in the end, you know you made a mistake somewhere. Checking magnitudes. If you work a problem and you find that a baseball is traveling at 3 times the speed of light, either the professor gave you a totally crazy non-physical problem, or you did something wrong. So if you get an unrealistic answer, that's a cue that maybe you should check your work again, all right? But this is another way to check your work. You get your answer and then you say, here's my answer. Here's Bernoullis equation, all right? Is there some special case? Is there some special limit where I know what answer I should have gotten? In this case, we said, yeah, I know what I should get if there's no flow, if the velocities are both 0. And so I try that limit, and I got the answer I knew I should have gotten. Had I gotten something different, I would have said, oh, I must have the wrong answer. I better check that again. So this is a good, it's cool that this is in Bernoullis equation, so it's worth seeing just because it's cool, but it's also an example of a way to check your homework problems. Get in the habit of checking your homework doing these techniques before you ask other people, am I doing this right? So that you are good at these techniques when it comes time to take the first exam. All right, anyway, so Bernoullis equation, turns out it's really useful, although it doesn't apply to a lot of situations. A lot of times our assumptions are just not valid. For example, I tried to make this class more realistic by making a problem with an airplane wing. I found some diagrams of the cross-section of a Cessna wing, and I tried to use that to calculate the stall speed, the slowest velocity the plane could go when the lift would just be big enough to hold up the weight of the plane. All right? So the idea is here that this is what I learned when I was a Cub Scout, that the air going over the wing has to travel further, so it travels faster, and you get this lift because higher, right? What does Bernoullis equation tell us? If the velocity goes up, the pressure has to go down, assuming the height doesn't change, right? If this one goes up, I have to compensate for it somehow, so the pressure goes down. So lower pressure on the top versus the bottom means that the pressure pushing on the bottom pushes harder than the pressure pushing from the top, and I get a net force upward. All right? So I took these diagrams, I worked up a great problem, calculated what the lift would be as a function of velocity, calculated the stall speed, and I was off by a factor of 10 from the stall speed listed in the manual for the plane. All right, so what's happening here? There's viscosity, there's turbulence. Also, one thing I didn't think about was the fact that there's no tube confining this flow. So the flow kind of comes off the end and does interesting things, right? And all of this broke the assumptions of Bernoullis equation, and so I got the wrong answer. However, Bernoullis equation is still useful. I learned about Bernoullis equation in airplane wings when I was a Cub Scout, and Cub Scouts didn't see the equation, but the general principle is still valid. When the velocity goes down, the pressure has to go up. When the velocity goes up, the pressure tends to go down, all right, neglecting things due to height change, all right? So even when Bernoullis equation isn't valid, the kind of information it gives us, the intuition about physics, is still useful, all right? And that is the end of what you need to know today.